Okay, good morning, everyone. Hopefully, your exam one is going well. You have until today at 5 o'clock to turn it in to me. And this time around, I'd like it if you just sent me a Blackboard message and attached your exam in that message. If you have trouble doing that, send it to my email, but also send me a Blackboard message saying that you sent it to my email address. Okay, so today we're starting the final section that I wanted to cover. Um, and this is over a branch of mathematics that's particularly close to me. It's called graph theory. And graph theory is what I study pretty much. For the last 10 years, I've been a graph theorist, and I have spent hours and hours studying graph theory. My PhD is in graph theory. So I have a connection to it, and hopefully you'll find it playful and entertaining as I describe it to you. Okay, so this is graph. All right. So I'm going to start graph theory by describing what's often referred to as the first graph of graph theory. And this graph originated from a problem that was posed, or actually more like a puzzle that was posed in Königsberg, Germany, quite a while ago. So in Königsberg, Germany, there's a river that flows through it, like water, okay? And then we have islands, and there's landmass on each side of the river. And then connecting the land masses are a collection of bridges. Okay. And these are big islands, by the way. Like there's entire neighborhoods here. There's like some markets here. There's a huge landmass here. There's a bunch of neighborhoods. And people would often traverse these bridges to go to the market or to visit friends and family. And over time, people started to wonder, just kind of out of curiosity, if you start on any landmass, so it could be like there, it could be there, there, there. Um, in fact, I'll go ahead and label them. So like I'll call this A, B, C, D. Okay. Starting at any one of these landmasses, can you travel each bridge once and only once? Okay, so let's like just maybe write that down. So this is the question. Um, Starting at any landmass, can you walk across each bridge once and only once? Okay, that's the question. Now, this doesn't seem like a mathematical question at first, right? Kind of like a puzzle. Okay, so for example, let me try with that. So maybe like I don't know. Someone tell me a landmass to start at. Somebody. A, B, C, or D. What was that?
B.
B. All right. So we're gonna start here. And let's walk somewhere. Where do you want to walk to? We can go to C, D, or A.
D.
All right, let's go to D. All right, so Now that we've walked across that bridge, since we're only going to walk across the bridge once, we cannot use that bridge anymore. Okay. So where should we go now?
C.
A?
C.
Oh, C? All right. So now we're down here. So now we can't use that bridge anymore. So we're just hanging out here. So we can't use that bridge, so we only can go up one of these bridges here. So maybe we'll walk up this one. And now maybe we can, where should we go now? We're back at B.
Back to A.
A.
We're at A now. So here. All right, so now we're at A. We can go to D, or we can go back to B.
D.
So if we go to D, right, we're going to get stuck, right? Because then we can't use that bridge, or that bridge, we're stuck. And I think if we didn't go there and we went back down to B, right? And we have to use that bridge. And then we get here and then we stuck because of those bridges. So hopefully you understand the puzzle now. We started at B and we tried to walk around and we couldn't do it. Maybe if we started at A, maybe we didn't take the right sequence of bridges, right? So in this problem, like notice that there's not any, like, do we care how long the bridges are? No, right? For this specific problem, like we don't care how long these things are. We just care if they're connected, right? Furthermore, we don't care about the angles that the bridges make between the land masses, right? So what this is telling us is this is not a geometric problem. It's not geometry, right? We're not concerned with distance. We're not concerned with angles. It's something different, right? And many people, they considered this question when it was first posed, didn't believe that this was a mathematical problem because it wasn't geometric. There weren't really any numbers involved. It was more about how these land masses are related. So people didn't really believe it was a mathematical problem until the famous mathematician Euler thought about it for a little while and realized that maybe there is something here that's kind of mathematical. This picture, though, it seemed that this picture was kind of, there's too much information. Right? There's all this water, there's this one's bigger than that one, and the bridges aren't exactly like this, they're kind of like this. But the picture, we don't need all that information. We're just concerned whether or not these land masses, how they're connected to each other. So we can take this picture and get rid of all the redundancies and draw something else. We can represent each of the land masses by a vertex, stealing some terminology from geometry. And then we can just connect them if there's a bridge. Okay. And then we can give them labels A, B, C, D. So this problem talking about bridges, and others, instead of bridges, we have what are called edges. So vertices and edges versus land masses and bridges. But all the relational information about this picture is now stored in this other picture. Except for now we've gotten rid of all the water and the thickness of the bridges and how long they are. Like, we could have drawn this any way we wanted to, just so long as the edges represented the relations between the vertices. So the plural of vertex is vertices, singular vertex. So this question now can be reformulated on this. And this right here, this is a graph. Okay. And in like, well, I guess it is formal, I'm just not writing it down. A graph is simply a collection, a set of vertices and a set of edges. So here we have a set of vertices, A, B, C, and D, and then there's edges, E1 here maybe, E2 here, E3, E4, E5, E6, E7. So a graph is simply a collection of vertices and edges, and that's what this is. So the vertex set for this graph here is just the A, B, C, and D. And the edge set of G is E1, E2, E7. There's 7 edges. So now, I think it looks a little bit messy right now, so because I want you to be able to see, I'm going to kind of erase those labels, but just know that those labels are there. So now the question is, starting at a vertex, can we travel along each edge once and only once? So if, for example, we started here, and maybe we can go this way like that, maybe go this way like that, maybe go down, we go down again, and maybe go back up, and then, but then we get stuck. We go to D, we're stuck, we go to A, we're stuck. Okay, so again, we took the problem in terms of land masses and bridges and turned it into a problem involving sets, where the sets are a vertex set and edge set, and we're asking if we can walk along each edge exactly once. All right, so the new question, I guess, which is just a graph theory way of asking the same question here. If we call this graph G, so starting at any vertex in G, can we traverse along each edge in G exactly once? So it's kind of like the graph theory version of this question. So yeah, like again, just to kind of draw it again and see if there's a way to do this. Again, it doesn't matter how you draw the thing, just so long as the relations are preserved. A, B, C. So what do you think? Can you do it? Is there a way to do it? Maybe, maybe not. Surely someone has a inclination of whether it's true or not. Or not true, whether the answer is yes or the answer is no. Anybody want to take a guess? Is anyone physically drawing it out right now, trying to figure it out? We got a no from George.
I'm sort of drawing it, but it's just trying to go through all the options right now.
Yeah. So it's actually like it. There's quite a few options, right? Like it seems that who knows, right? Like maybe we could count how many possible options there are, and then maybe we could write a computer program that would check every possible option. Right? But this is the nice thing about graph theory. And actually of all of mathematics, but with graph theory, it's the easiest to start. You can just draw a graph and then you have some question you have on that graph. And if you think that you can answer it yes, you just have to find it, right? So if you just keep on trying to find we want to visit each edge, right? So you just keep on trying it, you're going to run into things. You're going to run into, if it's not true, you're going to run into problems. And those problems should be with another no. Those problems should be like they should indicate why you can't do it. So let's just try it one more time on this graph here. So maybe if we start at C, and we go this way, and then we're at D, and then we go maybe out this way, and then we come back down. Now look what's happening here. We out, we come back in, but we have this one remaining edge here, right? So if we use that, okay, good. But now D and A both have one remaining edge going into them. So if we go in here, then we can't use that. If we would have gone in there, we can't use that. So it's almost like that one left over is causing a problem. Well, let's see if we can analyze this a little bit more. So I'm going to draw a kind of a little box here. And inside of here, there's going to be some graph. I'll call it G. I don't know what the graph looks like. I just know that there's a graph in here. And it just represents relations between vertices and edges. So, okay. Now, I would really like it if you communicated with me when I'm going through this argument. Okay, so suppose there is some vertex here. I'll call this V. Okay. And suppose that V has an odd number of edges coming out of it. Right? What does odd mean? It's 2 times an integer plus 1, right? So there's 3, or it could be like maybe 5. And we don't know where those edges go. We just know that there's 5 or 3 or 7 or 9 or 11, like some odd number of edges coming into V. Okay. Now, notice what happens here. Suppose that we don't start at V. Okay. Like V is just some vertex that we don't start at. Eventually, if we're going to walk across each of the edges, we need to come into V, right? Because we need to walk across these edges. So, okay, if we didn't start at V, maybe we come in here. Okay? And then we have to leave V to use one of these other edges, right? So maybe we like left out that way. Okay? But then there's still these edges come over here, right? So we came in originally right here, and we went out, but we have to walk across these other edges. So eventually we're going to come back in, maybe along that edge, And then we're gonna leave again. Maybe out that edge. But look what happened. What does this last edge here mean about our walk as we're walking around the graph? Where do we have to finish? If we're going to walk across each edge exactly one time, and we're walking around, so we didn't start at B, we came in, we left, came back in, we left. What does that last edge mean? What does that mean we have to do when we stop? Where are we stopping as we're walking around everywhere?
There has to be an even number of edges.
Hmm?
There has to be an even number of edges.
Well, this one, we're just assuming that this one has an odd number of edges coming out of it. And we didn't start there. And we just went in, we came out, went back in, went back out, and we're walking around. But if we're going to walk across each edge, we're eventually going to walk across this one, right? So eventually, we're walking across, and then we come back in along that edge. So what does that mean? Once we come back in, we're stuck, right? We're stuck there because we've already used up all the edges. So what I'm trying to show is that, okay, so if V has an odd number of edges, say, touching it, then if we don't start at V, we must finish at V. Right? And the reason is because if we don't start there, whenever we come in and we leave, we use two edges. Come in, we leave, two edges. And then when we come back in, leave, we use two edges. Because there's an odd number of edges, eventually we come in, leave, we're using two each time, which means eventually we're going to leave and there's going to be one last edge left. Which means the next time that we come into B, we're stuck. So if we don't start at B, we must finish our walk at B. So if V has an odd number of edges touching it, if we don't start there, we better end there. Okay. Now, this doesn't necessarily have to be the case if we start there, right? If we start there, then we could be okay. And again, I don't know where these edges go. I just know that there's an odd number touching V. Now, suppose that there's another vertex called W, and this one also has an odd number of edges coming out of it. Okay? By the same argument that we did with V, W, right? If we don't start there, we better end there. If we don't start there, we better end there. That's for any vertex that has an odd number of edges touching it. But what about there's another vertex that we call it Z? And this also has an odd number of edges coming out of it. So now, is it possible to walk across all the edges? If this is the picture, we don't know what's going on in here, but just knowing that these three vertices are in the graph, can we walk across each of the edges once and only once?
No,
And why is that?
because you would have to finish at two different places.
Exactly. That's exactly the right answer. Because if a vertex has an odd number of edges, then if you don't start there, you better end there. Because you always have that one left over. If you visit leave, you have two, and there's always that remainder, that one remainder. So, okay, if you started here, so if you start here, then, whoa, you didn't start there and you didn't start there. How can you finish at both of those at the same time? You can't. So it turns out that if your graph has 3 or more odd degree vertices, degree is the number of edges that come into the vertex, then you can't do it. If we look at our Konigsberg graph here, that has an odd number, that has an odd number, that has an odd number. They all have an odd number of edges coming out of them. So the answer is you cannot. And this problem is what started the field of graph theory. Before this problem, these relational type objects weren't really considered mathematical objects before this problem, right? Because here, this problem introduces that there are problems that you need to think about logically and mathematically that don't require necessarily caring about distance or angles. This is only a relational type of problem. Now, can someone think of, so this graph represented this like city bridge structure. Can someone think of a graph that many of you use or interact with every day? I guarantee you all of you interact with some type of graph every day. Well, let me first, before I go into that, let me give you the formal definition of a graph. Okay, let's see. A graph G is a non-empty set of vertices written V of G and a set of edges written E of G where the elements of E of G are pairs of vertices in the graph. Okay. So this is the formal definition of a graph. So Now here, V of G is called the vertex set. And E of G is called the edge set. This is the formal definition of graph. Okay, so let's look at an example. So let's say that V of G is equal to A, B, C, D, E. And then let's take an edge set to be, let's say, AB, AC, AD, DE, and then maybe DD. So that's a graph. Now it doesn't look like the picture that I had on the board a second ago, but this is how a graph is formally defined. It is just a collection of vertices and edges. Luckily, since most of us are visual when it comes to understanding things, we can draw a picture associated with this. And it doesn't matter how you draw it, just so long as the relations are all there. So for example, I can put like A right there. I can put B, C, D, and E. I just kind of put them in the plane. Doesn't matter where they're at. I just kind of arbitrarily chose these locations. And now I see that there's an edge AB. Okay. There's an edge AC. Edge AD. Edge DE. And an edge BD. I don't know. Okay. So notice I can like bend the lines, I can overlay the lines. The edges just represent relations. It doesn't matter if they cross over each other or not in general. So this is a graph. Okay. Now, there are different types of graphs where this is the general definition of a graph, but when you make specific requirements on the elements of the edge set, then you get certain types of graphs. So here, this is called a simple graph. So the best way to illustrate this, I guess, would be with a picture. Yeah. This is where I wish I had a larger board. Okay. So these are the main types of graphs that you'll see. So here, this is just a general graph. This is just a general graph. Notice that there's multiple edges between vertices, between two given vertices. So like here, there's two edges from there to there. Simple graphs don't allow that. This is a simple graph. Also, you can have self edges too general graphs, where the vertex just goes to itself. So for simple graphs, there's no multi-edges. Or loops. Where a loop is just a vertex that's sent to itself by an edge. Multi-edges are multiple edges between a pair of vertices. And in here we have a diagram, or a directed graph, where the elements of the edge set are ordered pairs, meaning there's a first and a last. And whenever there's a first and a last, it gives a direction between, so like that vertex is directed at that one, but that one's not directed at that one. Whereas here, that is connected to that, and that's connected to that immediately. So, an example of a graph would be possibly like routes for airlines, right? Where of course, if you go from one city to another, you can go from that city back to the other, and they're just connected, maybe. Or you can go from one city back to yourself if you have to circle back, something like that, maybe. A simple graph would be something like Facebook, where each vertex in the graph represents a Facebook account, and two vertices in this Facebook graph are connected if they're friends. That'd be an example of a simple graph. A directed graph would be something like Instagram, where you can follow someone else's account, but that doesn't necessarily mean that they're following your account. Okay. So the different types of graphs have different applications, and I think Facebook versus Instagram kind of definitely should be familiar to you. Or something like Twitter would be a giant directed graph. Okay. So far, so good. So, oh, and I guess like there's one more type, and this is related to like our final project in a sense. You can have what are called weighted graphs, where there are weights on each of the edges. And these weights can correspond to who knows what. Like, for example, flow along like a pipe, the strength of relation between two people, like if you take a survey. There's like a lot of dating apps use weighted graphs to kind of signify that there's a possible match between two vertices where the vertices are dating profiles. And then also another example would be for weighted graphs looking at matching donors with like organ donors with people that need the organ, in the weight on the edge connecting those two vertices is some measure of likelihood of compatibility between the organ donor and the person in question. So this is a weighted graph where there's weights on the edges. You can also have weights on the vertices as well, but for our purposes, we'll just look at weighted edge graph. And okay, so that's the basic definition of a graph. Those are some examples of where they might pop up in applications. Okay, so what time is it? 12:15. I think I'm going to go ahead and stop it there for today. I know some of you still need to finish your exam, and you're still working on that. So I'll stop that, stop the lecture for today, and then next time we'll actually look definitions on graphs and kind of go more into studying the structural properties that you can explore. All right.
We were just supposed to email the exam to you, right?
Yes, but I'd like you to send me send it to me via Blackboard as well. Just so I can have all of these exams ready to go in my Blackboard inbox.
How do we send it via Blackboard?
You can send it with a message. So if you open up
Okay.
Blackboard and you go to Blackboard messages,
Okay,
yeah, and then you can just create a message and send it to me. And you should be able to attach any PDF that you have.
cool. Will do.
Also, I would like to encourage all of you to visit my friend Sarada's YouTube account. And I'll post that YouTube account on Blackboard so that you can look at this. And this is a YouTube account dedicated to graph theory. I think it'll help a lot of you. All right. Good luck turning in your exam. Email me if you have any questions. And I will see you all on Wednesday.
Okay, bye.
Thank you.
Yeah.